our new NSF that she actually wrote while she was a graduate student, and she's now funded on as a postdoc based on a Fulbright that she did in Costa Rica. So as a little bit of background, Erin earned her PhD here in fall of 2016, so a lot of you guys might have seen her defense, and she'll kind of give you a brief version of that and follow up by talking about what we're really doing now. She was awarded the Sackett Prize for Innovative Research today, which she was nominated by 3 of her committee members for. To kind of give you a summary of what a successful PhD student she was, she published 10 peer-reviewed papers, 8 as first author during her graduate career. She did both her master's and her PhD here, with a Peace Corps stint in Guatemala in the middle. Her PhD research was funded by an EPA STAR Fellowship. She also received the Knight Endowed Fellowship, the Renee Bernstein Outstanding Authorship Award, and she got a really competitive Raymond Sarver Award from the American Society for Microbiology last year as well. So today she's going to talk to you about poop, everyone's favorite Thursday afternoon topic, and perception and how...
Right?
You weren't sitting at my table during the award ceremony. And how we're applying a transdisciplinary approach, which is not the same as interdisciplinary, I learned while we were writing this proposal, in Costa Rica. Erin.
Thank you, Maya. Thank you, everybody, for joining us today. I'm really excited to talk to you about one of my favorite topics, poop, and what we think about it. And so, for anybody that's ever heard me talk before, I always begin every talk this way. Fecal pollution is widespread throughout the world, right? In underdeveloped countries, 90% of wastewater goes untreated and it flows into surface waters. But in the United States and other more developed countries, we have problems with aging infrastructure. And as a matter of fact, our wastewater systems have gotten a D, and that's really bad. And because of this aging infrastructure, billions of gallons of untreated sewage enter surface waters each year. And that's without even talking about natural disasters that promote sewage overflow into coastal systems. And so with all of this fecal pollution, right, it's no wonder that it's one of the leading causes of illness in the world. And that's pretty much because of our interaction with water, right? So we use water for any daily activity, be it recreation or things that we just have to do, like eat, drink, shower, etc. The focus... Okay, so I mentioned wastewater is a big problem. It causes illness, but really it's not the wastewater itself, it's the pathogens that are in it. And there are tons of them, and these are like the most wanted pathogens associated with wastewater. We find parasites, bacteria, and even viruses. Viruses frequently are among the most problematic. And what's interesting to note is that I think many times when people think of wastewater pollution and illness, they really think about digestive problems, right? Like you get diarrhea, you vomit, but it turns out that a lot of these pathogens cause other health issues. Liver damage, death, meningitis, cardiac disease. There are lots of other diseases that are associated with wastewater pollution, and I think it's important not to forget that. Now, the focus of this talk is really the coast, and so there was an interesting study done in 2003, and they determined that there are over 1,444 deaths just because you swam in contaminated waters. And most of those deaths are actually from children each year. And to put that in perspective, I wanted to, everybody talks about shark attacks and risk, and some people, in this audience, right, we all know that there's no reason to be scared of sharks, but to put it a little bit into perspective, there were only 81 attacks last year, and only 4 of those caused death. While the number of deaths might not be outstanding, I think the number of cases of illness annually are outstanding. There are greater than 170 million cases of illness each year due to swimming in contaminated water. And because of that, coastal fecal pollution is really a global burden. When we take into account the risk of swimming and the illness caused by it, as well as the risk of illness caused to eating shellfish that were raised or cultivated in contaminated waters, we have a disease burden that's greater than 3 million disability-adjusted life years. That's a lot. And that equates to an economic burden of over $12 billion. And so, you know, we live in Florida, and why do we still go to the beach? Why do we run to visit countries that lack sanitation infrastructure to go to the beach? Jamaica, Mexico, Costa Rica, right? There are tons of countries that have beautiful beaches. Many of them are pristine, but often they're affected by wastewater pollution. And so why do we still go? Well, really, because it's fun, right? And as a matter of fact, 2 million people, 2 million person days per year are spent at coastal resorts alone each year. And so because we love to go to the beach, because it's important to coastal economies, because it's fun and it makes us feel good despite the contamination that may be present and the illness that could be caused, we need to monitor and make sure that the waters are safe. And so the United States and many other countries have monitoring programs, and these monitoring programs are based upon fecal indicator bacteria. And usually monitoring programs are done on a weekly basis. Sometimes they're done on a by-season basis, depending on the country. But all in all, the idea is that we use an indicator organism that isn't a pathogen to try to understand whether or not it's safe to swim. And usually countries either develop their own criteria or they follow the World Health Organization guidelines and say, okay, if we get this many fecal indicator bacteria per 100 milliliters, the beach isn't safe to swim at. If we have less than that, people can swim. So a little bit more of information about fecal indicator bacteria. They're used to study the fate of pathogens in the environment because it's really difficult to study the pathogens themselves. The tests are very expensive, and the fecal indicator bacteria are actually really easy to detect in water, and the methods are quite affordable. And as a matter of fact, this method has been used since the early 1900s to study fecal pollution. And the good thing about these indicator bacteria is that there is a proven correlation between illness, its presence, but unfortunately, this correlation only exists for beaches that are affected by point sources of pollution. That means like an actual pipe or something you can physically identify as being the source of contamination. And this correlation only exists for temperate latitudes. Tropics, subtropical zones are really a completely different beast. And that's because there are some drawbacks to the use of the fecal indicator bacteria. They can give false positive results in the presence of secondary sources. That could be animal pollution, which has a lower risk of illness to people. It could also be that after a contamination event, these bacteria grow and live and exchange genes with their cousins in the environment, and they can persist in the soil and sediments. And this is particularly problematic in tropical areas. Also, these bacteria are more susceptible to treatment. So they die off much more quickly in wastewater treatment. They die off more quickly when exposed to solar radiation, and so they often don't necessarily reflect the presence of pathogens. Last but not least, these guys are released in the feces of many different organisms, warm-blooded and even cold-blooded alike, and so it's often difficult to identify the source of pollution if you do find high indicator bacteria concentrations. Despite this, a lot of data are available from these monitoring programs, and we often don't know what to do with them, right? So like we're collecting these indicator bacteria concentrations, they have all these drawbacks, and at the end of the day, managers say, oh geez, what do we do? The concentrations are really high here, they're really low here, but we don't know why. And this is exactly what happened in Costa Rica when I met with the director of the National Water Lab. He showed me 15 or 20 years of data, and he was like, which indicator bacteria should we use, in your opinion? And which beaches are actually unsafe? And the truth of the matter is, we don't know. And so we have a lot of data, we don't know what to do with them. And not just because of the reasons I mentioned, but also because the results are received a day after the sampling event. And so that means everybody played at the beach, you took your water quality sample, and the next day you were like, oh man, maybe that was a bad idea to swim there. Like, there's nothing you can do to prevent exposure. On top of that, when you have beaches, right, that have multiple sources of fecal pollution and that often have hidden sources of fecal pollution like septic leakage, the correlation between these indicators and illness is off. And of course, I mentioned this already, but highlighting again, The presence of FIB in tropical regions does not correlate to risk as we know it. And so what do we do? So you always have to be thinking about the next step, right? We're using a technology and an idea that was from the early 1900s. I mean, that was a long time ago. There has to be something better that we can do. And so somebody, Nick Ashbolt and his colleagues came up with this idea for a holistic approach. And they call it a holistic approach because it implies multiple different tools to understand fecal pollution. They said, okay, instead of just doing compliance monitoring, why don't we take a step back, look at the beach, and look at the sanitary infrastructure? What's there? What's a problem? What could be a problem under different environmental conditions? And then they said, instead of doing compliance monitoring that you do on a weekly basis, why not do short-term monitoring? Specific monitoring in situations that we know will be high-risk situations, let's say extreme flooding events, rainfall, et cetera. And instead of just looking at indicator bacteria, for that short period of time, why don't we invest that money that we would use in a whole year to understand pathogen presence as well, using reference pathogens? And by doing that, you can use a tool, which is a computational tool called quantitative microbial risk assessment, in which you're able, based upon your pathogen concentrations and what you know about people's exposure to water, to determine the risk of illness. And from there, make management decisions that make sense. For example, a lot of times for people growing up in the south of the United States, I've been told that anybody living along the Mississippi River knows that if it's rained in the last 2 days, you shouldn't go swimming. So I think there are some common sense management decisions that can be made based upon this approach. So before I go into a little bit deeper on what we want to do in Costa Rica, I'd like to talk to you a little bit about QMRA, which is the Quantitative Microbial Risk Assessment tool. And these are basically the steps. There are 5. And the first step is pretty logical, right? You need to identify your hazard. What pathogens are there, and what concentration are they in, and what do they do? From there, you really have to rely on data in the literature to understand the dose response curve. And what does that mean? That means how many pathogens do I need to be exposed to get sick? And that changes for each person over time during their life. And so, you always have this curve of data. From there, you need to understand the dose that people are exposed to. And this is often calculated by understanding the concentration, in our case in water, and the quantity that people may be swallowing accidentally when they swim. And finally, with all of this information, we can calculate risk. And this is awesome and fantastic, but really, this risk characterization is only as good as the assumptions that are used to calculate the risk. And so this brings me to really want to talk about a project that I did during my PhD, because we were trying to use quantitative microbial risk assessment to understand the risk related to indirect wastewater reuse in Bolivia. And I know we're going to take a step away from the ocean and go into the mountains, but this collaboration that existed between Dr. Cairns, who is now a professor at Southern Methodist University, and I really set the seed for us to apply for the NSF grant. So we're going to Cochabamba, Bolivia. I know everybody's kind of sleepy, but does anybody know about Cochabamba, Bolivia here? Has anybody been to Bolivia? Anybody seen the movies about Bolivia? It's been a while, so it's not like it's like a blockbuster right now. Anybody? Okay, so Cochabamba, Bolivia is a really special place. It's beautiful. It's a valley in the Andes, but it's a complicated place as well, and it has been the stage for what we call water wars, right? And so Cochabamba has this challenging situation in which the city has expanded dramatically in the last 20 years. And at the same time, with population growth and industrial expansion, because Coca-Cola is there, beer factories are there, et cetera, and on top of all of that, they're receiving less and less rain every year, and there's less and less snowmelt. And so it's created this situation in which the river that flows through this valley has really poor water quality. Not only does it have very little fresh water being added to it, it has tons of wastewater being added to it. And so all of these black arrows are points at which we were able to identify wastewater pollution at a pipe source. And you can see here that the river itself is largely wastewater. And an engineering collaborator of mine who was the first author on the paper, his name is Matt, and he told me before I got there, he said, Erin, we should just make a stabilization pond system out of this river, because that would be the best way to treat it, and then we could use it. And I said, oh my God, Matt, it's a river. Like, I know you're an engineer, but come on, like, it should have biological life. We can't just like dam up and create these channels. But lo and behold, when I visited, it was true. This river wasn't so much of a river anymore. It really was an extended sewage lagoon. So this is complicated, right? Because there's farming going on in the valley. And typically in this region, farmers aren't the wealthiest individuals. And so individuals that have always used the river to cultivate their lettuce and their crops are all of a sudden have a contaminated water source. And we noticed that around these plots that some farmers were doing something very ingenious. Some people were pumping directly from the river. We were like, oh geez, I don't want to eat that lettuce, right? But then there were others that dug these ditches alongside the river. And the ditches would be filled with water from the river that had been filtered through the ground, which is called riverbank filtration. And then they were using this water, this well water, right, to see if whether or not, in order to be able to irrigate their crops. And we were like, well, geez, I wonder if that makes a difference with pathogen loading and risk of consuming this lettuce. And so we measured the concentrations of different pathogens, and blue you can see the viruses that we looked at, between the riverbank filtration well water and the river water itself, and we saw huge differences in pathogen concentrations, log orders of reduction greater than 3.5. And this made us really excited because the farmers had created this very low-tech, low-cost solution to a problem that they were facing. And with this, we were like, okay, well, it's great that we see these log reductions, but what does this mean for risk in the big picture? How can managers know whether or not this is safe? And so before we could make that calculation, we really had to look at consumption of lettuce. And so there are different ways you can determine how much lettuce a population eats, and all have their nuances and their drawbacks. So the first way we realized we could do this is if we took the annual amount of lettuce produced in Bolivia, the percentage of that stayed in Bolivia, divided by the population, right? And that gave us an annual consumption of 1.1 kilograms. The next way we can do this is by asking people how much they eat and going to restaurants to weigh the portion sizes. And this was done by our anthropologist. And so she went to the market, she went to restaurants, and based upon her calculations of what people told her, people are consuming 3.2 kilograms a year. Of course, the World Health Organization encourages the use of quantitative microbial risk assessment, and they provide lots of estimates for possible exposure. And they recommend 15 kilograms as your assumption for how much people are eating. It should be known that this value is based upon a European diet. And it's clear based upon our data collected from Bolivia that that's not the same. So with this in mind, we calculated the risk based upon the pathogen concentrations that we determined. Risk was put into units of disease burden, or dailies, per person per year. And dailies can be thought of as one loss of healthy life each year. So we have that on the y-axis. On the x-axis, we have the 3 different ways in which we calculated lettuce consumption. From the left, we have the percentage of survey respondents, the WHO example that used the 15 kilograms from Europe, and then the Bolivia population level calculation. The graph that you're going to be looking at has the median and the credible intervals marked. And then on the box and whisker plots, you can also see that the credible interval and the medians are marked. If we keep in mind where the WHO recommends as your maximum additional disease burden based upon eating irrigated lettuce or anything else, they recommend a burden of no more than 10 to the minus 4 dailies. And as you can see clearly, the Rocha River, which is highlighted in green, exceeds the disease burden allowable by the WHO, but the use of the river water, the river bank filtrated well water to irrigate the lettuce kept the disease burden at a minimum. And to further highlight that point, to mention that the use of the riverbank filtration wells allows us to meet the WHO guidelines. And if we put that into context from the current annual disease burden in Bolivia, if we use the river water itself without it being treated, you get a 37% increase in the disease burden if everybody ate lettuce that was irrigated with the contaminated water. But you only get a 1.1 increase in this disease burden if people are consuming lettuce that has been irrigated by the well water. And so despite the fact that this technology works and is within the health guidelines established by the WHO, we found when we asked people how they felt about eating lettuce that had been irrigated with treated wastewater, you can see most people felt very bad about that. And that really doesn't reflect the reality or the necessity that exists in Cochabamba, because there really aren't any other freshwater resources for irrigation. And so this really got me thinking, because I was wondering at this point, the project that we did in Bolivia was funded by a challenge grant that gave us $5,000 to do this research. And it was supplemented a little bit by an existing NSF grant that Dr. Mihalsik had. But in the end, this project didn't encompass what we could do with this data and the impact that it could have on people's decisions and on people's perceptions. And it really made me wonder, if we have data and it doesn't inspire change in perception or behavior, what does it matter if we have the data? And those types of questions really led to us writing the Coastal Seas proposal, and to do the project that we call MARA. Our collaborators, of course, Maya is PI, co-PI is Dr. Harwood in the integrative biology at USF, and we're accompanied by the same anthropologist from Bolivia who's now a professor at SMU, Dr. Carnes. And the abbreviation for MARA really comes from what it means in Spanish, because we're doing this project in Costa Rica. MARA stands for Medio Ambiente, Etnografía, Evaluación de Riesgos y Calidad de Agua, which is environment, ethnography, risk assessment, and water quality. And so as I mentioned before, right, everybody's doing this routine compliance monitoring, and each government establishes what they consider safe. So in the US, that's less than 36 enterococcus for coastal systems, and they say that FIB measurement is equivalent to less than 36 illnesses per 1,000 exposures. So that's the risk that we're comfortable with taking. So if we go from there and we think about this holistic approach that is probably more more pragmatic, but it's really lacking that perception aspect, and it's really lacking that practicality and that humanness to the project. And so this really got us thinking about creating a transdisciplinary approach in which we're equally balancing not the science and the water quality and the risk, but also what people think about it. And not just about what individuals think about it, but also really characterizing it such that we really understand the coastal system. And for us as oceanographers, we think of a coastal system and we just think about the environment, but anthropologists and political scientists and economists think about other things, and they're equally as important when it comes to making decisions, right? And so we really hope through this project to be able to characterize the ecological, political, cultural, and economic systems so that we can identify evidence-based feasible management options. And not only do we hope to identify them, we also hope to be able to communicate them effectively. And as I mentioned, this project takes place in Costa Rica, and that's pretty much because I went there in 2015 for a Fulbright. And I got to know the actors, I got to know the situation, and we were able to do some really great research that we're going to be building off upon. So during my 2015 Fulbright stint, We were able to do one of the first microbial source tracking studies in the region, and we were able to identify several human-specific source tracking tools. The pepper virus, HF183, was very useful there as well, and human polyomavirus. And so we're hoping to be able to use these tools in Costa Rica. We also determined that one of the most prevalent pathogens in wastewater was norovirus in Costa Rica. And so taking all of this into account, we spent a lot of time talking to the National Water Lab there, and we were able to identify a beautiful beach located close to the capital that is the most well-visited beach in Costa Rica, not just by foreigners, but also by Costa Ricans that want to get away for the weekend. And this beach, as you can see, has many rivers. As a matter of fact, it has 4. And rivers are awesome, and the beach is beautiful, but unfortunately in Costa Rica, 95% of the wastewater is directly discharged into surface waters. And that means rivers are polluted, especially if the rivers pass through highly populated areas. And so the National Water Lab, this is data that they have. They use fecal coliforms as their indicator of choice. And the rivers are highlighted in yellow, and they typically have concentrations of 10 to the 4, right? So 10,000 fecal coliforms per 100 milliliters. That's really high. You can't swim in that. You probably shouldn't even be on a boat in that if you go by the WHO guidelines for safe use of coastal waters. And the good news is that during the year, the National Water Lab has observed that concentrations of fecal coliforms along the coast where the river discharges, they're relatively low in the dry season. However, during the rainy season, the concentrations get really high. And I say here greater than 10 to the 2, but oftentimes they're equivalent to the rivers themselves. And so we don't have any data yet because we're about to collect data in a week, if all goes well. But I want to emphasize that this project is run by multiple organizations. It's frontlined by USF and SMU, but we have several collaborators in country that are working with us so that we can execute this study effectively. Marviva is an NGO, nonprofit, that's interest is in coastal conservation. The National Water Lab is AIA, and they have an awesome beach certification program called Bandera Azul. We'll be working with Costa Rican students as well as an EPA-certified lab, BCS labs in the United States. And in phase 1, we hope to collect a lot of data, not just the holistic water quality data that I mentioned during the dry and rainy seasons with FIB and pathogens, but also ethnographic data and epidemiology data. Then we hope to be able to characterize this risk, so the pathogen concentrations that we determine and the frequency in which people are bathing and admitting to swallowing water accidentally. We hope to use all of this information to characterize risk. We hope to be able to use the epidemiology information to double check our risk calculations as well. And then in the 4th year, we really hope to explore risk management possibilities. Do people need to not swim downstream of certain rivers, but they can swim at other parts of the beach? Is it a case in which you just don't go swimming within 48 hours of rainfall, or when winds are coming from a certain direction, because that influences the transport along the beach? We don't know, but we hope to be able to identify them. And finally, in the 4th year of this project, we're completely dedicated to the communication of results, not just in scientific conferences or in publications, but also within Costa Rica at a summit that will be held. And so through this project, we hope to do many things. Over the next 4 years, we hope to elucidate a little bit more the appropriate fecal indicator to be used in a tropical region, ideally one that's correlated with risk or pathogens. We hope to improve our understanding about human behavior and perception with respect to water quality. And we hope to understand the disease burden and how to minimize it. And last but not least, we hope that this study will be an example of how you can use a transdisciplinary approach to have a real-world solution to a very complex problem. Obviously, installing sanitation infrastructure in this area is the end solution, right? But that's going to take lots of years and lots of money, and in the meantime, many beach towns need to survive economically, And it's important that we are able to balance health risk management and economic stability. And so with that, I thank you very much for your attention. And who doesn't looking at baby sloths, right? So thank you again. Hi, yeah.
Which beach was it that you ended up selecting at the very end?
Are we still recording?
Oh,
We have to kill you.
okay, don't tell us. Let me ask you